Okay, I took way too long to draw this little picture of your little red sports car coming into a turn. So let's say you're going down Route 29 and you want to exit for downtown, and I don't know if you're going north. The downtown exit is a super tight exit curve. So let's just imagine that we are road engineers and we want to figure out what the speed limit for the road should be. So let's say that we've got a flat curve, right, a flat road, and the radius of curvature of that curve, right, it's not a circle, but at any point the radius of curvature doesn't get any bigger than 50 meters. So let's just treat it as a 50-meter curve. The velocity of the car obviously is always forwards, and it's going to have to accelerate when it goes around the corner. In dry conditions, and by the way, speed limits on roads are different in dry conditions and wet conditions. If you've ever gotten stopped for speeding in the rain and they tell you that actually you should be going slower than the speed limit, I think that's actually true. Anyway, so let's say we want dry conditions. Under dry conditions, the static coefficient of friction between your tires and the road is about 0.7. What is the speed limit for this curve? I will note that we've already done this problem in class previously, but we did it the other way around. We said if you're going a certain speed, what is the required coefficient of friction? But it's the same problem. I'm doing it again because I want to extend that to a set of problems. So these are the last couple friction rotation problems that we're doing in this chapter. So in order to do this problem, let's go ahead and assume that the car is going to be going around the curve at a radius of 50 meters. And let's draw a free body diagram of the car while it's in the curve. So I'm just going to approximate the car as a red dot and draw all the forces. Well, if it's a top view, the forces, what are the forces? But there's gravity and normal, but those are kind of hard to draw from a top view. But what is the force that's holding the car in the curve? The force that gives you the centripetal force that's holding the car in the curve. And I'm just drawing that as if the car is at the radius vector there. And that is a frictional force, right? If there was no friction, the car would just head straight along the green velocity line. But instead, because of friction holding the tires to the road, the car can follow the dotted line instead. So it's friction. And what kind of friction is it? It is static friction. If it was kinetic friction, the car would be slipping through the curve, which it could do. I mean, what's it called? Drifting, right? You could drift through the curve, but it's static friction that we want to keep our car in the curve. We don't want our car to start slipping. While the top view might be useful, it's probably better to draw either a rear or a front view. Let's go ahead and do a rear view. And what I mean by that is, again, I'll draw the eye to show where we're looking from, right? This is meant to be an eye. It is the way one draws an eye in some circles. And we're looking at the butt of the car. Okay, so from the butt end of the car, the back of the car, let's just draw it as red because we know it's a red sports car. What are the forces? We know that it's on the ground and it's flat ground, so the normal force is straight up because it's flat ground. And not all roads are flat, right? There's gravitational force because it's in the vicinity of a planet, the Earth in particular, and the frictional force is toward the center of the circle, which is to the right, looking from the back of the car. So we've got FFS. And that is a complete free body diagram because there is nothing else touching the car, only the road, and the road gives us both a normal force and a frictional force. So we now go ahead and do our typical Newton's second law problem-solving process. I'm going to put a coordinate axis plus x to the right, plus y up. Why is plus x to the right? Because the acceleration is towards the center of the curve. The acceleration is towards the center of the curve. And the center of the curve is this way, right? Is this way. That's the center of the curve. So the acceleration is that way. So I'm going to choose plus x in that direction and write f net x equals max, f net y equals may. And therefore, fill in the forces with X components on fill in this, then fill in this, then fill in this, then fill in this. So we do it every time. I don't think I need to remind you of that. But in order to do that, we need to take components of all the forces. In this case, all the forces are either in the X or Y direction, so we don't actually need to do any real components. We just have to recognize that in the X direction, we got plus FFS, and in the Y direction, we've got plus Fn minus mg, the weight of the car, Fg, and equals the mass of the car. I didn't give you the mass of the car. We'll get it later. We'll go look it up later if we need to. And the acceleration of the car. In the X direction, it's centripetal acceleration, so it's v squared over r. In the Y direction, mass of the car, and it's not accelerating perpendicular to the road. It's not accelerating perpendicular to the road. It's not moving up or down. G comes in the weight of the car, but it's not accelerating. It's not in free fall. It's not in projectile motion. Okay, so we can take those two equations, rewrite them here, and then say, ooh, okay, what are we asking for? We're asking what is the speed limit. That's the fastest speed before you slip, right? Before you slip. So that means that we are maximizing the static frictional force. So we're saying that the speed limit is going to be when the static frictional force is a maximum, and that's going to be mv max squared over r. Again, what FFS max is mu sub s Fn, and mu sub s Fn equals mv max squared over r. That gives us the maximum speed. And so, therefore, Vmax is equal to the square root of r over m times mu s Fn. Just solving that algebra. And we know r, we know m, we know mu s, but what is Fn? Fn is here, right? That's the y equation. From the y equation, we get Fn equals mg. Remember, Fn is not always equal to mg. It is on a flat road if we're not accelerating up or down, but it's not always mg. So from the y equation, we get Fn equals mg, and therefore Vmax equals that. And lo and behold, the mass cancels, r mu sg. Thank goodness that we don't have to make speed limits depending on the mass of the vehicle. So why are there speed limits for trucks that are different from the cars? It's because trucks are very massive, and so they're more dangerous at high speeds. And they're also they're three-dimensional objects that are more likely to tip over at high speeds than cars are. But the speed limit really doesn't have anything to do with mass. A truck will slip at the same speed that a car will slip. But again, let me do an aside here. A truck will tip more easily than a car. On a curve, if we have a truck, think about a truck which is tall going down that curve. Its center of mass, which we haven't studied yet, is higher than the car, which center of mass would be lower. It's more likely to tip on a curve. Actually, sorry, if you're, yeah, that's the direction it would tip if it's going around a curve. We'll talk about that when we get to center of mass a little more. Okay, so the velocity, the maximum velocity is, we can plug in numbers. When we plug in the numbers, we get 18.5 meters per second, which is about 40 miles per hour. Okay, miles per hour, which is what we usually do our speed limits in, 40 miles an hour. Now, what should the speed limit be? Should it be 40 miles an hour? No, engineers always build in room for error. They usually half the speed limits from what they should be, from what the maximum could be. So the speed limit on that curve should be actually 20 miles an hour in order to make sure we're staying safe. And indeed it is. I actually think the speed limit's 15 on the particular curve that we were referring to in the beginning. It's 15 or 20 miles an hour. So the maximum speed you would go before you slipped might be about 40 miles an hour, assuming that the coefficient of friction between your tires and the road, assuming you don't have bald tires, right? If you have bald tires, this number's going down and making it more easy to slip. Okay, now let's say that we are road engineers. We're done with that problem, but let's say we're road engineers and we want to improve the ability for cars to not crash on an exit ramp. So what do we do to the exit ramp to improve the speed, right? To allow us to go faster. Well, one thing we could do on an exit ramp, just look at Vmax. Vmax is equal to R mu S G. So we could build our roads on a planet where the acceleration due to gravity is bigger. Where we're all much heavier. We could all be much heavier. We could increase the gravity on our planet or move to another planet. I can't remember if Mars has more gravity or less gravity. We can look it up. Hey, Alexa, what's the acceleration due to gravity on Mars?
Here's something I found on reference.com. The force of gravity on the planet Mars is only about 38% as strong as that on Earth.
Okay. So it's smaller on Mars. So your exit ramps have to be slower on Mars. Okay. So G doesn't help us, right? Because we can't change G. Mu sub S, right? We want to increase mu sub S. You want to make your roads out of something that has a high coefficient of static friction. You want to make your tires out of something that has a high coefficient of static friction, or tires on road. But, we're pretty much stuck with rubber for tires and asphalt for roads. So we're stuck with that 0.7. We can certainly engineer materials that have a higher coefficient of friction. We can, and we do. But really, right, what the thing that you really have under your control is the radius of the curve. If you don't want to make a tight curve, a bigger radius gives us a bigger possible velocity. As a matter of fact, if I double the radius of curvature, by what factor can I increase my speed? Well, Vmax equals the square root of R mu sub SG. The only thing we really under control here is R. If I double R, what happens to the quantity Vmax? Vmax goes up by a factor of square root of 2. Let's algebraically make sure you understand how that works. We say, what if we change the radius? We're going to have a new speed. We're going to call it V prime. And the new radius is going to be called R prime, where the new radius is twice the old radius. So I can go ahead and plug that in, where the new radius is twice the old radius, 2R mu sub SG. So our new speed, Vmax speed prime, and that is equal to, you hopefully can see, that's equal to square root of 2 times the square root of R mu sub SG, which is the square root of 2 times the old Vmax. So we can only increase our speed by 1.4 if we double the radius. And it's kind of hard to double the radius of a curve because it takes up a lot of space. A lot of space. You certainly want to make the radius of curvature as large as possible, but it does take up a lot of space. So you got to balance those demands.